All right, so we're going to look specifically at, this is from page 77, we're going to look at problem 13. So if you've got your book, go ahead and look at that problem. I'm going to read through the problem and sort of take some notes up here as we go along. So one of the strategies we want to use when we're solving word problems is to kind of organize our information, and that's what we're going to do right here. So this is number 13 on page 77. Okay. In a certain medical test designed to measure carbohydrate tolerance, an adult drinks 7 ounces of a 30% glucose solution. So I'm just going to write this down as an adult. They're going to drink 7 ounces of a 20% solution. Okay. When the test, 7 ounces of a 30% solution. Okay, that's better. When the test is administered to a child, the glucose concentration must be decreased to 20%. So when we got to do this with a kid, we're going to use the kid strength version, which is only 20%. I didn't say how much. Here comes our question, so we're going to pay attention to specifically what they're asking us for here. How much 30% glucose solution and how much water should be used to prepare 7 ounces of 20% glucose solution? Okay, so it seems to me that we are actually going to do 7 ounces of the kid strength stuff. And then they're asking us how much 30% solution and how much water. Okay, you guys understand what a solution is? A solution is just some stuff that's mixed in with water. In this case, it's glucose, and glucose is just what? Just sugar. So here's kind of a pictorial representation. I'm going to try and draw a picture here. Pictorial representation of what's going to happen. We've got 2 beakers. Okay, one of them's got some glucose solution in it. One of them's got some water in it. And we're going to pour some from that beaker and some from this beaker in there, and this is going to give us our total solution. Okay. Now we're mixing it with water because we want to make it weaker. This is going to be over here. This one is our adult strength, and this is our water, and we're making our kid strength. So this one's going to be a 30%. This one's going to be 20%. And what percentage of glucose do they usually put in water? Trick question. 0. 0%. Water is just water. So do you get the idea of how this is going to work? We got the strong stuff. It's too strong, so we're going to mix it up with some water so it's not so strong for the kiddos. Cool? All right. Now, what's the question asking us? What are we trying to find?
How much glucose solution?
So how much glucose, which I've labeled adult here. This is like our glucose solution. And what were you saying? 2 things. Okay. So the other one would be what? How much of this we're putting in and how much for water we're going to put in. So what we're looking for are quantities here. I don't know how many ounces. So I don't know how many ounces here, and I don't know how many ounces here. But I do know that this is going to be 7 ounces. Correct? Get the idea? So whatever the red and the blue are, they're going to mix together. All together, we're going to have 7 ounces. It's a question of, is it 4 from the red and 3 from the blue? Or is it 6 from the red and 1 from the blue? That's what we got to figure out.
I thought the adult already had 7 ounces.
Yes.
Now let's think about this. If I put 7 ounces of the adult mixture in and I'm trying to get 7 ounces out from the kid mixture, then it's all going to be from the adult mixture, isn't it? We're not going to have any room for any water.
But we do have 7 ounces of the adult. We're just figuring out how much.
Do we have 7 ounces of the adult? Is that what they said? Let's read the problem again. This is a little confusing. So,
It's saying the adult.
in a certain medical test designed to measure carbohydrate, an adult drinks 7 ounces of a 30% glucose solution. So I read that to say that when an adult takes this test, the adult drinks 7 ounces. That's not all that we have. We got an unlimited amount to use, we'll assume. The kid's also going to drink 7 ounces, but we just got to make sure that the kid's version is weaker. So I don't think we're going to use 7 ounces of the adult stuff to make the kid's thing, because we need to weaken it. We need to put some water in We're going to use a little bit less than 7. We're going to mix some water, and that's going to make it a little bit. Make sense? All right. So we got a nice idea of what's going on. Now the next step is key. When you're solving a problem, you need to understand how the different numbers that you're given to and that you're working with relate to one another. So what I'm going to do, this next strategy is we're going to step away from the numbers in the problem, and we're going to look at the situation of just concentrations and solutions in general. I'm going to come up with a general example that'll be easy for me to understand, just so I can wrap my head around the math of what's going on here. So the idea of the solution, again, is that you've got some mixture of stuff. There's some amount of pure stuff in there, but then there's some extra stuff that's added in, some water. So I'm going to come up with sort of an easy example. I'm going to say I've got 100 ounces of a solution. And I specifically picked 100 because we're dealing with percentages, and 100 is really easy to work with when you're dealing with percentages, right? 100 ounces of a solution, let's just say at some concentration, just let's make something up, say, I don't know, 15%.
Go with the problem.
This has nothing to do with the problem, it's just the same kind of measurement, the same concept. I'm just trying to wrap my head around what's the deal with the whole solutions and concentration. So if I've got 100 ounces of solution, remember this is both the pure substance mixed in with some water, and I got 15% concentration. Can anybody tell me how many ounces of actual pure stuff is going to be in this big jar of solution? And keep in mind that this jar contains both pure chemical and water. I got 100 ounces in my jar. How many ounces of it are the actual pure stuff? Not the water, just the pure stuff. How many ounces? 15 ounces because it's 15%? Does that make sense? That's what concentration means, right? That means that 15% of this 100 ounce thing is going to be the pure stuff. And the rest of it, the other 85 ounces, just water. Does that make sense to you? Do we need to do another example like this? Or do you feel like you understand how concentrations work? All right, so let's test and see if you really do understand how concentrations work. 100 was easy to deal with. Let me give you a number that's not so easy to deal with. I'm just going to make something up here. Again, this is not the actual problem. 73.1 ounces of a solution. Let's stick with 15%. Can you tell me how much actual pure stuff would be in here? We got 73.1 ounces of the solution, but not all of that's pure. Some of it's just water. How much of the pure stuff would be in there? Get a number for me? 10.9. I want everybody to kind of verify that using your calculator. Is that what you're getting to? If you round it up, it'd be 11 point something, or it'd be 11.0. All right, so let's say we round it up, but now it's 11.0. Okay. Are we all getting somewhere in that neighborhood, though? Okay. So we feel like we understand what's going on here mathematically in terms of solutions and concentrations and pure substances. This is an important step. Sometimes you need to step away from the numbers in the problem just to make sure you can wrap your head around the math here. This next part is really the key. Okay, I'm gonna write out what we did to get this. I took 73.1 times. You didn't multiply it by 15, did you? You multiplied it by 0.15 to get 11.0. So here's the key step. Write this out in words. What is the 73.1? What did that represent in this example? That was the amount of what? The amount of what? That was the amount of the solution? Okay, we took the amount of the solution and we multiplied it by 0.15. And 0.15 was what? It was 15%, but in words, what is that? That's the concentration expressed as a, not as a percent, we changed it into a decimal. And when we multiplied those together, we got 11.0, and 11.0 represented what? The number of ounces of what? The amount of what? The amount of pure stuff that was in there. So what we've done is we've kind of created an equation, a formula, if you will, that we can use to deal with these different numbers that we're given. From this, we're directly going to build a table. And now we're jumping back to the numbers in our problem. Now I'm going to do 3 rows in my table. Why 3 rows? Because we had 3 beakers in that picture that we looked at a second ago, right? We were mixing 2 of them together to come up with a final product. This is going back to our original problem. So this is going to be, our first one is going to be our adult strength. And then we're going to mix in water. And that's going to give us our final kid strength stuff. All right, and this gives us a place where we can organize our information in a table, and it helps us because it helps us use different rows of the table to come up with other values in the table. So let's start filling in some numbers here. So give me one of these boxes that we can fill in right now. The amount of solution?
Or you could do concentration.
Okay, let's do the amount of solution. You said that first. Do I know the adult, the water, or the final?
Final.
We know that the final is 7. All right, we also know some concentrations. Give those to me as decimals. For the adult, it was 0.3. And for water, what was the concentration of water again? For water, yeah, there's no glucose in the water. And then for the final product, we're going to have 20%, so that's 0.2. So 20% and 30%. And I think that's all the information we're going to get out of the problem, unless I'm mistaken. There is one more number that we could fill in this chart. Anybody know what it is? The amount pure for the kid. This one right here. Now, how do you know that? They didn't tell us anything about that. We can multiply it. That's why we wrote this equation up here, right? That was the whole point of coming up with that example, because now we know that whatever the amount of the solution is times whatever the concentration is has to give us the amount of pure stuff that's in it. 7 times 0.2 is 1.4. So we've got that worked out. Okay, cool. Now, I think that's all we're going to get out of this. We're going to look for a variable we can throw in here. And usually you want to put your variables in the spot for the thing that you're trying to figure out. Are we trying to figure out how much of each of these solutions we're going to use, or are we trying to figure out what amount of pure substance is in each of those 2 solutions? How much we're going to use, the amount. So we're going to be using these 2. So we can put variables in here and here. Now we could use X and Y, but some of you know a little trick. You can be clever about this. What can I use instead of this Y here? Anybody know? Maybe you've all seen this trick before. X has to add up with something to give us 7. What's that something got to be? Let's play a game. I'll tell you what X is, and you tell me what goes in the other one, okay? So, and remember, they got to add up with 7, okay? Do it as fast as you can. You ready? Let's see how good you are at this. If X is 1, then the other thing is 6. If X is 5, then the other thing is 2. If X is 3, then the other thing is 4. Okay. If X is X, then the other thing is... Somebody said it. Now think about it. What did you do to 1 to get 6? 7 minus 1 is 6. 7 minus 5 is 2. 7 minus 3 is 4. 7 minus X is 7 minus X. So we could put 7 minus X in here. Have you seen this trick before?
No.
When you got 2 things that have to add up to something, we call one of them X. Now think about it. Whatever we use up here, we've got to use the rest of it here. Right? And they got to total up to 7. So if I use 3 here, then 7 minus 3, that means it must be 4 here. Now if you prefer to do it with X and Y, you can. You're just going to end up with a system of equations, but you can handle that. All right. Now we can fill out the last 2 blank columns, or last 2 blank cells in our table. What's this going to be the amount pure for the adult stuff?
Wait for X.
0.3x. And 7 minus x times 0 is 0. Cool. Table's filled out. Now our last step is going to be just to look and see if we can find an equation within this table. For example, would it make sense that if you added these two things together, the total would be this? Does that make sense? So there's an equation. 7 plus, x plus 7 minus x equals 7. Now, if you try and solve this, you're going to get 7 equals 7, which isn't very helpful. So that one's not very useful. Now, if we had used x and y, we would need to write the equation x plus y equals 7. That would be one of our two equations. Would it make sense to add the concentrations together to get the final concentration? No, you don't add percentages. Okay, that doesn't work that way. So that doesn't make sense. Would it make sense that the amount of pure stuff in both of those things combined would be the amount of pure stuff in the final products? Yes. So here's another equation. 0.3x plus 0 equals 1.4. Now that looks like something that we can solve. And that's what we're going to do. We'll solve that, and then we'll know what x is, and then we'll know what the amount of solution for the adult stuff is. We can figure out the amount of solution for the amount of water, and we'll be able to answer our question. Okay? And then we're done. So I know that took a long time to talk through, but sometimes you got to stop, pull back from the problem. This step that we did up here was really important when we were looking and kind of looking at a simple example just to make sure we understood the mathematics of how this situation works. Questions?
Yes.
No, you're not going to guess. You're going to look at each one of the rows, and you're going to ask yourself the question, what makes sense? Does it make sense that when I combine two amounts of solution and add them together, that's going to give me the total final amount of the solution? Yeah, that totally makes sense. In the real world, that makes sense. Does it make sense when I combine two concentrations together that I get the final concentration? Well, you can see that the numbers don't even make sense there, so I'll ignore that.
So we're using both of those equations, right? Is that what you're saying?
Well, if you try and solve this one, the x and the negative x are going to cancel out. You're going to get 7 equals 7.
Oh, yeah.
That's not going to be very helpful. This one you could solve. What's your question?
No, I was just wondering like
Okay.
think what would it
Are we okay with this one? All right, so let's look at 10. And again, the real challenge in 10 is going to be to understand the vocab. Hey, I need a favor from you guys. I need a desk, one of those desks, or that empty desk needs to go out in the hall, or if you guys could shift make that here. Somebody make that happen for me, please. Thank you. You guys might need to move. Sam, can you kind of move so you can get through there? Thanks, Jonathan. Appreciate it. All right, we're going to read through number 10. Again, let's read through it together, and we'll take some notes as we go. City government has approved the construction of an $800 million sports arena, so it's going to cost us. It's going to cost us $800 million to build this arena. And I'm just writing 800 because when I look through this problem, I see all the dollar amounts are written in millions. So I'm going to ignore the millions part, and then I'll just make sure in the end of my answer that I tack a million onto the final answer. Okay, so that's how much it's going to cost. Now, the next couple sentences get a little bit confusing. It says up to $840 million will be raised by selling bonds that pay simple interest at a rate of 6% annually. Okay. You guys know what a bond is? It's a pretty easy, pretty simple idea. All right? Let's say I make a deal with you, okay? You're going to give me $100. I'm going to give you a piece of paper. And the piece of paper is going to say I owe you $150 in 2 years from now. Okay? So basically I'm selling you a piece of paper that says I owe you $150, but not for 2 years. So I take the $100 that you gave me, I do whatever I want with it. When you come back in 2 years, you hand me that piece of paper, I gotta hand you $150. Get the idea? Pretty simple idea. It's like a loan. It is a loan, that's what it is. Basically, I'm borrowing $100 from you. I just gotta pay you back plus a little bit extra to make up for the fact that I borrowed. Yeah.
Basically,
So it's kind of a guaranteed. Well, it's not guaranteed because if she gives me $100 and then I flee the country, then
okay.
right. So there's no guarantee that the person that you sold or that you bought the bond from is going to be around to cash it. But the idea would be yes. So when you think of a bond, it is a loan. We're talking about the city is going to take out a loan to build this arena. Okay, so there are two sources. We've got to raise. We need to take out loans. We're going to take out $800 million in loans, and we've got two sources for our loans. One of them is by selling bonds. I'm selling a bunch of pieces of paper to people, and we're going to have to pay them back eventually. And we'll pay them back a little bit more. And the interest rate that we're going to pay is 6% interest. Now, what is the $480 million? Is the big question. Is that how much we're going to borrow from these people? Does it say that we are going to borrow $480 million from these people?
No, you're gonna raise.
We're going to raise the money, so that's the kind of the borrowing portion of it. The bonds are going to bring in $480 million. Read that sentence very carefully, especially the two words that come immediately before $480 million. Up to $480 million. Are we going to borrow $480 million? No, that's the maximum. Maybe we will. We're certainly not going to borrow any more, but we could borrow less. 480 is the maximum amount of money that we're going to be able to get from selling bonds. Our other source of loans is going to come from an insurance company. That's the next sentence. The insurance company, it says the remaining amount up to $640 million. So the $640 million max, up to $640 million. I lost it. There it is. Will be obtained by borrowing money from an insurance company at a simple interest rate of 5%. Right? All right. So are we going to actually borrow 480 and 640? No, because then we'd have way too much money. We only need 800 million. If I borrowed both of those amounts, we'd be over 1,000 billion. If we have $1 billion, we don't need that much. We're going to borrow some from this, and we're going to borrow some from this. These are the maximum amounts that we're going to be able to get out of those two things. The final question asks, determine whether, so this means this is going to be a yes or no answer, determine whether the arena can be financed so that the total annual interest is $42 million. So our total interest is $42 million. All right, so this is kind of tough to understand, which is why I'm going over this. The idea is we need to figure out how much am I going to borrow from the bonds? How much am I going to borrow from the insurance company? So that my total interest from both of them combined is going to be $42 million. Once I figure those things out, then I have to figure out whether that's going to work or not. Now let's say I solve here, and I find out that I need to borrow $600 million from bonds. Is that possible? No, because the max was 480. So if I find that I have to borrow $600 million from bonds, how am I going to answer this question? No, it is not possible. Okay. Let's say I figure out for the bonds that I need to borrow $400 million, and from the insurance company I also need to borrow $400 million. Is that possible? Yes, those are both within the maximum values for those two things. In that case, the answer to the question would be yes, it is possible. Okay? We are not going to use these values at all until the very end of the problem. Once we figured out exactly how much we're investing in bonds, and how much, how much we're getting out of bonds and how much we're getting out of insurance. Okay? You understand that those 480 and that 640 are just maximum values. That's just the limit on what we can borrow. We're not going to use them because we don't know for sure how much we're going to need to borrow from each. Questions? All right, this one's confusing. All right, now let's do that thing again where we come up with a concrete example and make sure we understand how investments and interest works. I'm going to go back to $100. Let's say we borrow $100 from your rich Uncle Rick. Maybe $100 million if he's really rich. We borrow $100 at, give me an interest rate, just make something up. 4% interest. How much interest are you going to owe rich Uncle Rick after a year? How much? You borrowed $100
$4.
at 4%. We're going to owe $4. All right, so we don't owe $4. That's easy, right? All right, now here's a tougher one. Still 4%. We're going to not borrow $100. We're going to borrow $162.51. Can you figure out for me, please, how much interest we're going to owe rich Uncle Rick at the end of this? So you're multiplying it by 0.4? 0.04, yeah. 0.4 would be what percent? 40%. That would be mean Uncle Rick, charging you that much for interest. And 162.51 at 4% interest is going to give us, what's our, $6.50. All right, so I feel like we understand how interest works. Let's write out our equation. This is the amount borrowed. And that would be money. Times, what's the 0.04? That's our interest rates. And we're expressing that specifically as a decimal. Equals, what's the $6.50? That's the interest we owe. And that's in dollars. Okay. That's going to give us our table. Let's start filling this in. We're back to our values from our problem here. And I don't have them. I can't see them. They're way up on the screen. So you guys, I'm going to rely on you guys. Remember, this is another situation where we've got kind of two things that we're going to be combining together to give us a total amount. Remember, we're borrowing from bonds. Whatever version you want. Make sure you write it on there.
Can I take this out?
Yes, please. Bonds from insurance, and then we're going to have our total value. So help me fill out this table. What do we know? We know the rates anyways. That's probably the easiest thing to fill in at first. What's our interest rate for bonds as a decimal? 0.06. And for the insurance loan that we're going to get? 0.05. All right, what else can we fill in here? Yes.
Bonds could be accepted insurance.
Let's get some numbers in here. There were two other numbers in the problem. Now we're going to ignore the 640 and the 480, but what were the other two numbers?
The total would be
800. That would be the total amount borrowed, right? Because we've got to build the arena. It's $800 million. We've got to borrow exactly that much. We're going to borrow $800 million.
We got 42.
And then 42. Where's that going to go?
Total interest.
Total interest. All right. Now this is looking pretty good. I think Now, we're actually going to ignore this for this problem because it doesn't make sense to add up interest rates. It just doesn't work that way. So we'll ignore that one. I think now it's time to start putting some X's in. We want to figure out how much we're going to borrow from the bonds for sure, and also how much from the insurance. So let's call this X. And do we want to call this, for the insurance, we want to call it Y, or do we want to get tricky like we did in the last one? Don't call it Y. What can we call it instead? If they got a total 800, what can we put there? 800 minus X or X minus 800?
800 minus X.
800 minus X, are you sure? Think of an example. If X is 100, if this was 100, this would have to be, because they got to add up to 800. If this is 100, that would have to be 700. 800 minus 100 is 700, yes.
Why does it have,
I'm thinking of an example just to make sure it makes sense, right? Again, sometimes you just got to give yourself a concrete example. It gets confusing with all these variables. So I don't know that X is 100, but I can test to make sure that this makes sense. If I put 100 in here and 100 in here, I get 100, 700. Yes, that makes sense. Okay. All right, multiply across. 0.06x. And we need to distribute that 0.05 to the 800 and the negative x. That's 40 minus 0.05x. And here comes the big question. Where are we going to get our equation? The right-hand column? And you got to ask yourself this question. Does it make sense that the interest I paid from one thing plus the interest I paid from the other thing would equal the total amount of interest that we have to pay? Does that make sense? All right, then there's our equation, and we're going to solve it. I'm going to leave the last step up to you. Remember, you need to solve for x. That's going to tell you a value that you borrowed from bonds, and then you can also plug it in here and find a value that you would borrow from insurance, and double check that they add up to 800. They should. And then go back and answer the question. If you remember, we're only allowed to borrow this much from bonds and this much from insurance. If either of those values go over those maximum limits, then we're going to have to call off the deal. The answer to the question will be no, it's not possible. Okay? Question? Good question. The question was, are we always going to be adding down the last column? And the answer is not always. Okay? There are going to be some problems, for example, where you're going to have a rates times time equals what? What equals rate times time? Distance. Distance equals rate times time, right? You guys have all used that formula before. Distance equals rate times time. So you're going to see a problem where a woman's going jogging. And she's going to go out and she's going to go back. Okay, she's going to go out someplace to a certain point, and then she's going to run back. She's going to run slower on the way back than she ran on the way out. Tired, right? Now, in this case, there is no need for a total column, because what do you know about these two distances? If you're going out to a particular point, and then you're coming back to where you started. No. If I start at my house here, and I run out to the tree, there's my tree, awful tree, and then I run back, what do we know about those two distances? They're exactly the same. So in this case, I would take this distance instead of equal to this. But you have to think about what is being represented here. Are they equal to each other? Do they add up to something in particular? Do they subtract sometimes to get something? For most of the problems, you're going to see either you're going to have a couple columns that will be equal to each other, the rows that will be equal to each other, or that you'll add up to get the total. Okay? And that's it. I'm sorry that took so long, guys, but I hope that will help you set up. You've got 10 problems in that assignment that are all very convenient to set up in tables. I'll take any questions tomorrow. Thanks for your attention.